Alright, so welcome to DETEC. It is a paper about detecting 20,000 classes using just image level supervision. Now, traditionally, in an object detection framework, we couple together two problems, right? We couple together the drawing of the box, which is called the localization problem, and the naming problem, which is basically naming the object category at hand. And when you couple both of these together, what this means is you need detection datasets where we have both the boxes labeled and the classes labeled. This creates this sort of very expensive annotation process. So typically detection datasets have very small number of classes, like Coco has 80 classes, even Elvis has just 1,000 classes. Compare this to something like ImageNet, which was collected a decade ago, has 22,000 classes with 14 million images. Now what you can think of is basically how can we leverage something like say OpenAI's CLIP model to improve the naming capabilities of a detector. We tried to do that, it works really well, it actually was almost number 2 on the Elvis leaderboard when we tried it out, but this model still makes very silly mistakes. For example, that image that you see over there, it detects a lion, it gets the box perfectly, but it calls it a bear. And for a bunch of other classes we saw similar things. So naming is actually the big problem over here. Now, what we find is basically that if you look at the number of class distribution for the number of image distribution for classes, lion is actually a rare class in Elvis. We have only 43 images of lions. And in fact, all the lions in Elvis are actually statues of lions or soft toys of lions. And that's actually why it does not generalize to these natural images of lion. If you look at a dataset like ImageNet, you'll get a lot of images for lion, like about 1,500 images or so, and you'll get a huge coverage of the number of classes as well. So essentially, we can leverage the fact that image level datasets exist, and we can just try to solve the naming problem. Because as you observed in that example, it's really good at getting the boxes, it's really bad at naming things. Now, so here comes the actual sort of setup. We have a detection dataset with like 1,000 classes, where we have both the box tables and the class tables, and we have an image level dataset where we have 22,000 classes, but we do not have a single box table. And we want to use both of them together to train a detection model. Now, in a traditional setup, when we have both box tables and image labels, box tables and class tables, it's very simple to train a detector, right? You take the RPN, you ask it to predict the box, then you train the classifier head to basically classify amongst the classes. It's pretty easy. But what happens when you have basically a image where you do not have a single box label? Now, in this case, prior work tries to do some kind of pseudo-labeling. The RPN predicts like a bunch of boxes, you know that this image contains like a person and a sports ball, and you try to assign basically the ROI to this particular image. This is pretty error prone. The image might contain 10 people, might contain 20 people, you don't know which exact ROI is the sports ball and so on, and essentially all of these errors creep into your model and it destroys performance. In our case, we have a very simple trick. We completely sort of sidestep this pseudo-labeling process. At training time, when we get an image that has just a class label, we fix the RPN. So say the RPN predicts 1,000 boxes. We throw away those boxes. We inject a fake bounding box, which is basically the entire image, and we use the ROI features from that image, and we use that to update the classifier. Okay, so in this entire process, what we did is we did not update the RPN, we only used it to update the classifier. And we just used this fake bounding box to create ROI features. So whenever we get detection data, we train both branches. Whenever we get classification data, we just train one branch. And with this, now at test time, we show that this detection model can actually detect classes for which it has never seen a single bounding box. Now compared to methods that were doing pseudo-labeling, it does really well. On benchmarks like Elvis, it can outperform them sometimes by even more than 10 percentage points in AP. We can further improve this model's performance by actually thinking of the classification layer as a text embedding, and we can replace that with an OpenAI CLIP model's text embedding. And with that, we now truly get a model which is beyond 20,000 classes. It's actually a completely open vocabulary detector. And now when evaluated on like these other detection datasets for which we've never seen a single training image or ever like seen their class distribution, it comes very close to detection models that are optimized for that image distribution and that exact vocabulary. And finally, here are like a few detection results. It does pretty well on this image that I clicked of my co-author. It detects his lanyard, detects his socks, detects his watch. Here is basically like an image, people trying it out on Twitter. It works on paintings, it works on cartoons. There's a web demo as well, so you can basically like upload images. So here is basically, again, Rohit, and you can see like, basically it's detecting his shoes, it's detecting his lanyard and his tag and so on. And these are classes that it has not seen in different datasets. Also it predicts masks as well, so it basically detects segmentation.
Can I ask a question? industry.